1965, off the coast of Virginia, a scout rocket with a payload of 370 pounds left its launch pad at dawn. After following a nearly vertical trajectory to an altitude of 130 miles, it hovered for a moment, then plummeted back to Earth. No headlines were made. Reporters weren't even present. But the mission was recorded an unqualified success. How these sounding rockets are assembled and launched, and how meaningful information is gathered from their experimental payloads, is our story today on Science Reporter.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15.
Hello, I'm John Fitch, MIT Science Reporter. Today we're out at Wallops Island on the eastern shore of Virginia, where the National Aeronautics and Space Administration has its main launch site for its small rockets and scientific payloads. You know, 20 years ago, nothing as big as a baseball could be launched without the whole world's undivided attention. But today, we seem to have transformed that mysterious void, at least its nearer reaches, into our own private backyard laboratory. Out there, at the rate of almost one a day, scientists launch the minor experiments that test and measure the world about us. But it is, in fact, their results, when gathered together, that form the real launch pad of any major space achievement. From this very grandstand area, scientists, technicians, and even just idle observers have had a chance to watch space history in the making. The sounding rockets, launched quite routinely from this barren shore, vary in size from the 6-foot HASP to the 72-foot Scout. They can send hundreds of pounds of instrumentation as much as 3,500 miles into space. Since the end of World War II, these workhorses have sent back valuable information about the composition and characteristics of our upper atmosphere. From heights above the ionosphere, they have also been able to return information about stars and galaxies. With the bigger rockets, Wallops Station has had a hand in major orbital launchings, too. In 1959, they began a 2-year series of tests on the Mercury spacecraft that included the renowned flight of 2 rhesus monkeys, Sam and Miss Sam. During these same years, they launched and inflated the trial series of plastic spheres that preceded the Echo communication satellite. Currently, as part of our international cooperation project, Wallops is also orbiting satellites like the Canadian Ariel that have been developed in other countries. For an introduction to Wallops Island and to the kinds of research going on here, we talk first to Mr. Robert Krieger, director of Wallops Station. Actually, it goes quite fast.
At the end of World War II, there was a need for research in flight, in guided missile aerodynamics, and particularly in the transonic aerodynamic region.
This would be going through the speed of sound, breaking the sound barrier?
Going through the speed of sound. There were wind tunnels that could do research at subsonic speeds, that's below the speed of sound. And there were some wind tunnels that could do work above the speed of sound, or in the supersonic region. But there was no way to obtain valid research data at transonic speed, or the speed of sound, Mach number 1.
Better to use a rocket than to build a wind tunnel that would go through this area?
You didn't know how to build a wind tunnel that would go through this area at that time. So Wallops was established with these ideas in mind, to do research in these areas. We were established in 1945. As far as we know, this makes us the first establishment that engaged in research by means of rocket-propelled test vehicles. We are a civilian agency, and also, as far as I know, we're the only rocket shooting range that's completely managed and operated by civilian personnel.
And what kinds of rockets, what kinds of experiments take place at Wallops?
Well, primarily sounding rockets, space probes.
These would be things that go up and then fall back down again?
Go up more than one Earth radii and come back to Earth, suborbital flights. And finally, small scientific satellites. The small scientific satellites are fired on Scout, which is the vehicle that the performance curves are shown here from a firing a few months ago.
So you do put satellites into orbit?
Oh, yes, we have about 9 satellites in orbit by now.
Whom do you do this work for?
Oh, we work for, of course, the other NASA centers. We do experiments for more scientific groups and the other arms of the United States government, the Defense Department, the Bureau of Standards, the sort of thing. More recently, we have been doing a good deal of work with foreign governments who are trying to get into space research by training them and assisting them technically with their early flying.
With the hope that they'd be able to go back home and set up their own races?
Yes.
I see.
Most of our experiments, or at least a large percentage of them, are from the universities. The university scientist brings his payload here to Wallops, and we apply our know-how and our facilities to put his experiment into the right environment in space.
This is blockhouse number 2 on Wallops Island. Experiments from across the country and around the world are brought here to be assembled into rocket payloads. During its final stages, no one other than the technicians working on it are allowed in the room. To learn about an experiment using what is called a mother-daughter payload, we talked with Dr. John S. Nisbet of the Ionosphere Research Laboratory of Penn State University.
Well, tonight we're going to fire this payload up into the ionosphere and try and measure some of the properties of the ionosphere and find out what controls them.
Now, just what is the ionosphere?
The ionosphere is a region above the Earth. It starts about 60 miles above the Earth and goes way on out about 1,000, 2,000 miles. And it is controlled by the sun. The sun's radiation comes in and splits up the atoms of the air. It breaks off the electrons from the atoms, and they're able to float around freely in this upper region.
Does that actually affect us here on Earth?
Oh yes, it affects us in lots of different ways, because all the relations between the sun and the atmosphere affect us. In particular, of course, the ionosphere affects radio waves, so it's very important for transmission.
Well, now, why do you need a rocket to do this experiment?
Well, of course, you never fire a rocket if you can do an experiment any other way. It's very much easier to do experiments with ground-based methods, because the effort you have to put to get a successful rocket experiment for the amount of data is quite enormous. But there are some things you can only do with a rocket, and those things are mainly the kind of experiment where you want to study something in a lot of detail. You want to be able to investigate things in a vertical line above the Earth. You want to study the vertical gradient, or perhaps you want to be able to measure particles that just don't get down to the surface of the Earth. You only do when this is the only way to do it.
Well, what about using a satellite?
Satellites are very nice because they last for a long time. You can get experiment over a year or so. But the trouble with them is that you get variations in the local time, you get variations with altitude, you get variations with latitude, longitude. All these things then affect your measurements. It's very difficult to sort out the result of a satellite. Now, this experiment we're doing tonight, we want to measure at one particular time. We're looking for one particular effect, and the only way really to do it properly is with a rocket.
I wonder if you'd tell us how your payload is put together.
Yes, I put a diagram over here. Now, when the rocket goes up, all these bits here are assembled. You have the main rocket mounted onto here, and then this bit sits on top here, and this bit sits on top here. Now, once the thing gets up into the upper atmosphere, up into the ionosphere, we break the whole payload up. We separate all these sections. The first bit to go is the main rocket in this section here, and then we're left with these two bits sort of floating freely up in the upper atmosphere. And then finally we split this part from this part, and this is the key experiment. This is the transmitter section. It's got 3 radio transmitters, just like a normal radio station, and it sends radio waves back to this section here. Now, what we're going to do then is measure the wavelength of the radio waves in the ionosphere. The wavelength is controlled by the electron density in the ionosphere. We've got a whole lot of other gauges up here that are going to tell us things about the incoming photoelectrons and the electrons that we have up there. We're going to put all this data together, and then we're going to transmit it back from a telemetry transmitter in here right back to Wallops Island.
You now know, of course, how to assemble the fins, how to torque the different items into place. But let me impress on you that the most important point is to be assured that you have a proper rotation in the vehicle so that you have a proper roll, which gives you good trajectory. What we're going to do
To lift experiments into the upper atmosphere, Wallops Station can call on a whole family of rockets, ranging in size from a 6-foot Arcus to a 72-foot Scout, capable of putting satellites in orbit. Some of these rockets are put together here in Assembly Shop 1. Engineers from a number of countries come to Wallops to receive training in rocket assembly and launch as part of NASA's program in international cooperation. Here, project leader Jack Hurdle explains the rocket alignment procedure to Mr. Ricardo Valenzuela of Argentina and Mr. Ivan Miranda of Brazil. Earlier, we talked with Mr. Valenzuela about his country's space program.
And therefore, the first...
Well, Mr. Valenzuela, what kind of space program does Argentina have?
Well, Argentina space program came from 5 years ago when the people in Argentina launched the first vehicle made in Argentina.
Oh, really? Well, what was this for? What was the purpose of the rocket?
Well, the purpose of this rocket was to make some measurements in the atmosphere. And the first principal purpose of the first one was ballistics determinations in the flight trajectory.
Where do you launch these from?
We launched this rocket from Chamical. Chamical is an old-fashioned Air Force base we put in shape for this purpose.
Is it on the edge of the water, or do these...
No, the Chamical base is just in the middle of the country.
So when they fall down on land?
Yes, we fire against Salt Lake.
Well, what brings you to the United States and to Wallops?
Well, the purpose was to be an Argentine member in the ExaMetNet program.
What is that?
Well, this is an experimental inter-American rocket network program.
What is it to do? What is it for?
It is for make some meteorological measurements in the upper atmosphere from 30 to 60 kilometers.
And who is participating in this?
The countries who participate in this program are the United States of America, Brazil, and Argentina.
And you will all be firing rockets at the same time?
Yes, we'll perform a launching operation together in the same time.
Well, then what are you learning here at Wallops?
Well, I'm learning the standardization procedures for this particular operation.
Oh, I see. So that all these rockets will be the same. The experiments will be the same in these three countries.
Yes, we use the same rockets.
I wish you'd tell us about what you think will be the future of the space program in your country.
Well, as our space agency says, we are going to make some launchings, special launchings, scientific launchings in meteorological area, but perhaps someday we can put a satellite into orbit.
After an experiment and its rocket have been assembled on the launch pad, the center of attention shifts to the control room miles away at the main base. These men are monitoring the many parts of the picture which must all be successfully pieced together before the launch can take place. Among those who must be satisfied that all is in readiness is the range safety officer, Mr. Lloyd Parker.
John, most of our work takes place weeks and months before each launch. However, during the launch operation, one of our major concerns is shipping in the area in front of us. Now, here is a local map of Wallops Station. Show that we face on the broad Atlantic Ocean. We are some 150 miles south of Washington, D.C., and some 90 miles north of Norfolk, Virginia.
Oh, I see. You fire out over the Atlantic, then?
Yes.
And these rockets actually land in the water?
Right, and our impacts occur. We have a multi-stage vehicle, so we have impacts which occur at various ranges out in the ocean. Now, we surveil for these ships by means of an aircraft which is flying overhead and looking at these ships with radar. He calls their position back to our radio operator, and then they are plotted upon the board so that we can evaluate the hazard to these ships. As you see here, we have a ship which is entering the hazard area. Now, in order to protect this ship, we must either hold up the launch operation or move the impact to an area where there is no longer a hazard to these ships.
Now, how can you move the place where the booster falls back in the water?
Well, these vehicles are launched from a launcher which is steerable, and we can actually point these vehicles in any direction we desire. Now, this is necessary because of wind, so these vehicles correct into the wind, so therefore we must compensate for wind. And in the same procedure, we can also move this impact to any point we so desire.
Did you ever hit one of these ships?
No, thank goodness.
Well, now, why couldn't you just send him a radio message and ask him not to go into that area?
Well, it so happens that we have no communications with these people, and they are tankers and commercial vessels and also fishermen. And if they were catching fish, I doubt they would move anyhow. Providing we can find an area which is large enough to contain the hazard area of the booster, and it is clear of ships, we can then successfully complete our launch.
All right, how about this discharge?
Although there are many people, like the range safety officer, who can say no, there's only one man who can say go. He is the flight director, Mr. Robert Duffy, who has supervised nearly 2,000 rocket launches at Wallops. We asked him to describe a typical launch for us.
We're here to find out for our viewers.
All of the activities which are required to conduct a countdown, launching, tracking, or recovery operation are coordinated from this room. Each of the smaller operations which fit together to make the overall operation have personal representatives in this room.
Right, so you mean there might be somebody here whose sole responsibility is to make sure the payload sitting on top of the rocket is still all right?
Yes, that's right. In fact, this fellow over here is in contact with people in the blockhouse who switch the payload, and by reading instruments are able to tell the condition of the payload. And he even talks to another fellow in the telemetry building who is monitoring the radio signal which the payload is putting out.
See, the payload sitting on the rocket is sending out radio signals just as it will when it goes up.
That's right. And he's able to tell you the condition of it right to launch. The fellow over here is talking to the launch vehicle preparation people. They're working in the blockhouse and on the pad preparing the launch vehicle. He keeps us advised and their status, and also them advised of the status of other operations. The Wallops project engineer here is kind of our local expert on the job. He has been with this project since it was decided that it would be launched at this range. So he knows all the little details in the special requirements which are required to make this a successful experiment. So he really acts in as the assistant test director in this case. Down on the other end, you have the man who takes care of the details of the countdown. He makes the countdowns notices. He keeps everyone advised of any schedule changes. He takes care of frequency coordination and answers telephone and takes care of real details.
Well, now, what about you as test director? Where do you fit into this?
I occupy this position here.
You're really at the apex of a tremendous pyramid of people, I imagine. There are people out in the field, and they have their representatives here, and they all in turn report to you. Is that the way it works?
Yes, that's right.
How many people would be involved in a typical launch?
Well, depending upon the complexity, from 100 to 150 people.
Must be quite a job just sort of keeping in communication with all these people.
Yes, it is. And it's easy to see that we use an elaborate setup of communications. We rely on the telephone, intercom, radio, or any other means that we can dream up to accomplish this.
What about the television and monitors in several places here?
Yes, we have closed-circuit television. We have cameras at strategic locations, are able to control them and observe what's going on in the different areas. Some of our other systems, too, such as programming and timing, keeps the count going and ties all the records together. The displays up here come from a computer, which is able to take digital information from the radars or other sources and make different computations and give you displays such as you need to run an operation.
Well, now, assuming that none of the 100 to 150 people that are involved have said no go, then what happens next?
Well, if everyone is satisfied, we launch the rocket, and once it's in the air, we get information back by telemetry, which sends data down by a radio link, and also we track with radar, which tells us the position of the rocket during the different periods of flight. I would like to show you one of our radar platforms. On these radar platforms, we have pre-plotted the trajectory which we expect this rocket to fly. This view shows altitude and range. The rocket takes off from here, moves up along this trajectory, kind of a side view.
See, that's already there, and then a pen will actually follow when it is flying along the same path.
The view over here is kind of a top view. It's an XY plot. It shows a trace across the Earth's surface which the rocket trajectory makes. In this case, it's going to fly due east. The other lines on here are used to determine that the rocket's flying on a safe azimuth. The northern limits here are used to protect land masses to the north, such as New York, Boston, and such.
Glad to hear that.
The southern lines then take care of the southern U.S., Caribbean islands, and South America.
And then normally the vehicle would be flying right along here. Well, what happens if it does deviate sharply off to one side?
Well, if it becomes an unsafe flight, then determined to be dangerous, then the range safety people would have to take action. From this console, they are able to send the commands directly to the launch vehicle. And they would send an armed command and a destruct or fuel cutoff, as would be required for the case.
They either could blow it up or cut it off and just let it drop back into the ocean.
That's right.
Does that have to be done very often?
Well, in over 5,000 launches, we've had to take destruct action less than a half dozen times.
Well, assuming everything is proceeding normally, what happens while it's on its way up?
Well, when the rocket is in flight, we are usually receiving experimental data then by means of telemetry.
This is the telemetry building where information from rockets and satellites is received and recorded. I'd like to have you meet telemetry systems engineer, Mr. Frank Boykin.
John, telemetry systems receiving begin with our antennas. These are located outside on the roof and in different places. Let me show you a couple of these.
I want to see you have closed-circuit television to watch them.
Closed-circuit TV so that we can slew it in and take a look at the different antennas so we can tell just how they're functioning during an operation. Let me move over here and I'll show you how the controls work. We have a manual control of this antenna which we can move it around as you see this way. Let me focus over here a little closer to us.
But now, you wouldn't try to follow a rocket that was blasting off?
No, actually it would be pretty hard to follow one manually. So these antennas have capability of automatically tracking a signal. That is, once they acquire a signal, they will lock onto the signal and follow it.
I see.
And we also have another method, a program method, such as we would use on our Tyros weather satellite. We know its pre-described orbit, so we set up a program and then slave the antenna to this program and allow the antenna to track on through the program. Bob, would you start the program for us? Here you can see the antenna is following one. This is a simulated type pass. It could be a Tyros pass,
right,
or it could be an actual launch from the island.
Now, what kind of a signal do you receive on these antennas?
Well, we have a receiver here. Let's see what it would sound like. There's the noise you would hear. I'll see if I can tune it in and get a signal.
Sort of a singing sound.
Yes, there's your signal mixed in with some noise. It would be a weak signal. Also, we have a visual display of the signal on this oscilloscope.
It doesn't look like much more than noise.
No, actually, this is actually a telemetry signal with the individual data channels on a composite carrier signal.
Well, you might be measuring a lot of things simultaneously, and it's all put together on one single channel?
Yes, much like your TV system, where you have the picture and the audio on a common channel. Except we have many more channels than you would on just the two on TV. We take our signals from this location and we run them through a receiver, and then the signals are piped into our readout room. Would you like to step over and we'll tour through our readout room? These signals are brought into the readout room and used in two forms. We have one form we record on these tape recorders, which you see right over here.
Right.
And we also process our data in real time. We take the signal you saw in the other room, the composite signal, and we feed it into these discriminators. These will separate the individual channels of data out so that we can further reduce and display each individual channel. We might...
Oh, I see. You mean actually you might have temperature coming out of one and pressure out of something else?
For different experiments. Over here, we have our plotboard display, which is actually a display of some signals. We have one running right now of one of the old scout vehicles we fired. You can see here the first stage is firing and going up. This is a plot of acceleration. Here the first stage is stopped thrusting and the acceleration is dropping off. And down here we have a pitch program, which is showing us that our vehicle is pitching properly.
Of course, it changes its course.
These things are, of course, in real time on an actual operation, and we feed this data to our range safety officer, who uses this along with the plot board data from the radars, which you saw a little while ago, to determine if the vehicle is flying properly.
Well, what about the experiment, though?
Well, the experiment we have displayed over here on some oscillographs. This is a plot of a bioscience project we had some time ago where we shot a rat into space to see from a biological standpoint how he would do. Here you can see these little pips represent his heartbeat.
Oh, really? Well, what happened to the rat in his
Oh, the rat is back and living fine. We recovered him, sent a ship out and recovered him. Here is actually a picture of the rat. And this is the reduction of the data from the telemetry that has been formed by the experimenter. And these are his results.
So that's sort of the end product then
yes,
of your
this would be the end product. And here are some other ones which show different projects we've done. Now, some of these may take this telemetry data and further reduce them in a computer. They would smooth the data and reduce it out in a computer form.
These would be the various experimenters having gone back to their universities or to their NASA laboratories, worked on the information, and finally come up with what they wanted, the finished report.
Right. This would be an example of the raw data before it is actually processed.
Well, thank you very much, Mr. Boykin. This has been extremely interesting. Today, we've been visiting Wallops Station at Wallops Island, Virginia, to learn more about NASA's program for rockets and small satellites. I'm John Fitch, MIT science reporter.